Goran is here. Our next speaker is Professor Goran Georgeovich. I think now is the time, so his title of his talk is on quadratic and almost quadratic p-adic and adelic path integrals in adelic quantum mechanics. Please, Goran.
Thank you.
Maybe you can put full screen.
Thank you, Chairman. Thank you to the all organizers, in particular to Wilson, Branko, and Igor for organizing this web conference. Thankful for invitation to give a talk. And I will, as Zoran told, I will present some results on quadratic and almost quadratic p-adic and adelic path integrals. We were motivated by application in the cosmology, in particular in some models of inflation, what I will present at the end of the talk. A part of this research was done together with my younger collaborators, Danilo Delibašić, Dragoljub Dimitrijević, and Milan Milošević. So, since the very beginning of establishing of p-adic and a little bit later adelic quantum mechanics, path integrals was accepted as a very good tool or one of the most important tools for considering dynamics on non-Archimedean spaces. So I will present briefly here introduction and motivation, and I will put accent on the previous and the new results related on, as I told, on the p-adic and adelic path integrals for quadratic systems. There will be presented motivation which come from earlier papers of Ashoka Sen with tachyon fields, and after that applied to Randall-Sundrum approach to inflation. So, one of the main motivation for developing path integrals was application in quantum cosmology. As we know, the Planck scale phenomena should be considered not only on the standard real or Riemann geometries, then also on non-Archimedean and non-commutative ones. So one of the main aspects of the modern cosmology is different models of inflation as one of the crucial scenario from which we can get information of the very early universe. And in this case, it's very important to have both real and p-adic dynamics on the table, and after that, if possible, to be combined in a very general adelic approach. As I think everybody knows in this community, one of the main reasons to use p-adic numbers came from the fact that field of rational numbers, which contains all observational data, is a dense subfield of R, but it's also in the case of the p-adic numbers. So as it was shown in the pioneering papers of Valovich, Vladimirov, and many other people, the general mathematical methods and laws should be invariant of interchange between real and p-adic numbers. At that time, and also in the new investigation of quantum gravity, we know very well that the measuring distances around the Planck's length and also other physical means, other physical values, means that we should not restrict be only on Archimedean geometry, then also on the non-Archimedean geometry. So, as it was proposed in also one of the papers of Valovich and Vladimirov, and after that extended by the paper of Zelenov, Dragović, and our group in Niš, it's quite reasonable to extend this Feynman path integral on the non-Archimedean space. As it is known, there are two basic analyses on the p-adic fields. It means with mapping of the p-adic variables to classical case, to also to p-adic number, and from p-adic number to the quantum numbers. What means in our case that we enter to the world of the quantum world. So in the last case, the usual complex valued functions with p-adic variable can be transferred by the additive character. And in this case, one of the crucial factor is to have locally constant functions with compact support, which appear to be the vacuum state in the corresponding p-adic valued field theory. Of course, it's also possible what was developed mainly by Hrenikov. We can consider the quantum mechanics on the p-adic mapping, but it was not our cup of tea until now. So to develop Feynman path integrals in the new fashion, in the new way, we have to remain and to remember that we have very well-defined Haar measure and integration. And unfortunately, till now, we are restricted only to the Gaussian p-adic integrals. And it was one of the main problems we were faced in our investigation in the last few years. So just to remember, maybe for the people who are not very familiar with that, we have real analogus of integrals in the real case, which was presented here, here, and with the p-adic one. Of course, we have this Legendre factors here, p-adic norm, and as I told in the very beginning, we have the character. So if there is anybody who will like to have some explanation from this side, I will come back and repeat it, but I think we can go now further. So the crucial for the establishing of quantum mechanics was to find that this kind of triple, it's a crucial and enough for establishing a minimal model. So we have the space of functions we are using for representation of the our dynamic world. We have this kind of operator here, which mimics the non-commutativity and basic non-commutativity between coordinates and momenta. And finally, we have the dynamic operator of evolution presented on the p-adic fields. Later on, it was shown basically by Branko Dragović that this kind of generalization we can do in the adelic case, and that it can very well fitted in that real case can be very well fitted in this way to the adelic generalization. So the crucial point here, I would say, it is to present and to implement the operator of evolution through its kernel, and to define the eigenvalue problem in this case. So we cannot extract the energy level in the way as we used to have in the standard quantum mechanics, then rather in this case, as values appear here in the character and the eigenvalue problem for the operator of evolution. So the main problem in computation of p-adic transition amplitude, or the Feynman path integral, is given here. So the question is how to calculate the p-adic path integrals or adelic ones, and can we do it, and for which kind of models we can do it. It was first proposed by Zelenov to do it in a way that we, in a sense, a guess or propose the corresponding action and then to approve its existence. The next approach was proposed by Branko and myself, where we calculate the classical action in p-adic case and then shown that it is possible to extend the Witt-Moretti classical formula in the real case to the p-adic and adelic case. It can be done in the practically in the any dimension, which later was developed by Dragović and Rakić. Here it is the general formula for a three-dimensional case. I think it's clear. It is clear how this formula can be interpreted. So here I give some kind of the summary that adelic quantum mechanics and this triple is composed of adelic Hilbert space, Weyl quantization of complex valued function, and unitary representation of an adelic evolution operator. In this form, it's very important to have the form of adelic wave function. So we have that adelic quantum mechanical or even field theory state has to be represented in this way, where on the first place we have the real wave function or real vacuum. And after that, we have this finite and infinite product of characteristic omega function. In this case, we can have some kind of the perturbative state, which has to be finite one. Okay, this is the general approach. In the beginning, it was considered a few particular model, like a free particle harmonic oscillator, which was done in this case by Volović, Vladimirov, Zelyanov, and Dragović, and after that it was also discussed for the particle in constant field, free relativistic particle, and the first non-autonomous system was a harmonic oscillator with time-dependent frequency. So for the moment, I will skip this part of the adelic quantum cosmology. I can come back if it is important, and I will come to the let's say the main point now. Well, we were or let's say in a case I was motivated by the appearing of very interesting features of tachyons in inflation. And just briefly, idea of tachyons was appeared by Sommerfeld even under other name, like 100, let's say 5 years ago. And after that by Feinberg, who give the name to the particles which should propagate faster than light. In the language of the special relativity, it means that we are faced with the particles or with the phenomena which can be understood as the particles with a square of mass smaller than 0. It is straightforward to see that in this case the particles has to propagate with a velocity bigger than 1, or in this nomenclature, or in this noting, where 1 is denoted to the velocity of light. Sorry. So this perspective, of course, is out of date, and today we considered tachyon as a special state which is unstable and which goes to the local minima and not to the local maxima. And in this case, we have the second derivative of the potential, which then play a role of the mass, square mass, or it means that we have this effect that the second derivative is less than 0, what it means that we are in the local maxima, and then we can consider it the condensation of the depth field, which called tachyon field, in the particles with a square mass effectively less than 0. In the standard case, in the literature, we can consider the standard Lagrangian with the tachyonic field given in this formula here, and to have this interpretation that I mentioned just below. In any case, we are faced with a canonical form of the Lagrangian with a standard kinetic term with some kind of the potential, and etc. etc. Just note here that we have, let's say, a wrong sign of the potential here, which is given in this form. So, as I told, Shoka-sen proposed an effective tachyon field action for Dirichlet brane in string theory, and we are faced here with a bit strange action, or with a strange form of Lagrangian here, where we have a square root of the form which reminds us to the kinetic term, and then it was multiplied by the potential. So in this case, we will choose T to denote the tachyon field, and V T for the tachyon potential. It is so-called Dirac-Born-Infeld action, and it belongs to the non-standard Lagrangian, as I explained before. Please note that this kind of the dimensions of the space can in principle be any one. So it can goes from 1 to n, and n can be 1, 3, 4, whatever you want. In the physical case, let's say with the more reasons, we can have 25 dimensions, or in the supersymmetric case, 10 or empty or 11 dimensions. So this action leads us to this form of the equation of motion for the tachyonic field. And this is a general form of equation of motion which does not depend on the potential, concrete potential we are considering. As you can see, it is a nonlinear differential equation. It means that we are faced with a non-quadratic action, and with a non-quadratic Lagrangian system, what we know from the before. So in this case, also in the real or p-Adic case, it's very hard to handle this form. So we are asked ourselves, can we transform equation of motion from the class of the non-standard Lagrangian to the Lagrangian in the canonical form, or if it is possible to get it in a quadratic one, and then they use the machinery which was developed before, either by ourselves or by colleagues that I mentioned, or maybe even I didn't mention everybody who contribute to that. So then we come to the idea to use the canonical transformation, and in this case we generate the new and, let's say, old variables with the momenta and corresponding momenta of the tachyon field, and we generate a function as it was presented here on the slide, and we have to find the form of the generating functions g, or corresponding the function f. When we apply the canonical transformation, we can see that our starting equation of motion, this one, got an even more complicated form. However, now we are in position to ask about this guy in front of the t dot square. Is it possible to find the generating function and keep the classical canonical transformation to be equal to 0? It appears that it's more useful to try to find inverse form of the generating function f, And in this case, it's related to the Lagrangian, in which we have the original form of the potential. However, we introduce here a new variable x capital. In this case, the equation of motion reduces to an let's say excellent form, so that we can, using the inverse generic method, to find the corresponding standard type of Lagrangians in which we have to present the canonical form. Examples. I will present here one of the potential, which is important because it gives a very good agreement between the observational inflation parameters and the Planck results from the inflation. So this particular potential is physically significant in this way. So let's use the potential that I presented here, where T is the tachyon field, and in this case we can find the form of this of this generating function. Let me say that all presented here, it is related in the transformation from the field theory and n dimensions to the one-dimensional form, which is the straightforward, or it's a straightforward procedure, but it is a standard approach when you transfer the field theory to the classical mechanics and then to quantize it. So in this concrete case, generating functions G, presented as a product of momenta and this part of the generating functions f minus 1, give us the results, which is presented by inverse sinus hyperbolic functions. And now we get it's a general formula for this kind of the potential, and straightforwardly we can obtain the quadratic Lagrangian. So please have a look to here, and we have the form of the standard kinetic term, and the harmonic oscillator with the wrong sign. It is inverse harmonic oscillator, which have a repulsion. So it's very interesting that all dBi Lagrangians in this form presented in the classical case has a repulsive character. So in a sense, an inflation is guaranteed by this approach. So now it's not a big deal to calculate the quadratic action, and because this form of the function is valid for all real or all p-Adic cases, we can calculate immediately the transition adelic p-Adic or adelic amplitude, which is presented here. So we got the standard form for the quadratic Feynman path integrals, in which have the Legendre symbol. We have the standard norm, either p-Adic or real, so in a case p-Adic, and we have here in the adelic form we have the character with the classical action for the cosinus hyperbolic in this form. Sorry. So we are now in situation to test, does we have an adelic form, and this can be done in the standard, again in the standard form. It means that the operator of evolution presented here by its character has to give us the characteristic omega function or the vacuum state. So also it's very well known that we have to integrate over the field of the p-adic integers, or that our tachyonic field with the tilde here has to be inside the p-adic unity ring. Using p-adic Gauss integral, I would say that we benefit from the results, basically, I think, given by Vladimirov in the mid-80s. We are able to calculate and to try to see under which condition we have the vacuum state or the basic state in the quantum mechanics, in the p-adic quantum mechanics. So here are these results, and we calculate it for a number of the potentials. For instance, I present here not for the cosmic hyperbolic, then for any inverse power law potential. So you can find here the results, and that this is satisfied in the standard form of the existing of the vacuum state. Here I present it for the particular case n equal 1, and we show that we can go to the infinity. So you can use it for the any power. What is interesting? I will just come one step back. So the crucial formula is here on the bottom of the slide. You see, we have the for the potential t tilde square, and depends of the potential you use, and depends of the n that I presented. The all potential will be transferred in our local equivalent Lagrangians between t tilde power 1 and t tilde power 2. So between the constant repulsive let's say field, or called the repulsive force, and inverse quadratic oscillator. That's a very interesting feature. Okay, so in general, we are faced with the following cases. In one case, we will have that this variable tau, which in our case represents some kind of the time variable, is bigger than 1. In this case, we don't have the vacuum state. In the case that t is equal 1, this is the form of the vacuum case, and from here we can extract and read for which parameters of the potential we can have the vacuum state. And the third most important and most useful one, it is the form in which we are inside the p-adic unity, and for the time sector in which we have the existence of the omega function or the characteristic and vacuum state. And now we are considering a little bit more physically interesting situation, because till now we were in the one-dimensional case. Now we are dealing with the dBi in four-dimensional case, in a sense, kind of the Minkowski space-time. So we are starting again with the tachyon-like Lagrangian, with some kind of the tachyonic potential, and this form of the kinetic energy. Okay, we use the standard form. However, now we make a step further, because we want to see how this model will be fitted in the case of the expansional space-time. So we introduce the scale factor, which is not, of course, constant, is untrivial case, and we consider we consider what kind of Lagrangian we can associate it with this one dBi, because we don't know how to quantize it in this case. Unfortunately, in this case, we can present the results only for p equal 1 modulo 4, because in other case, we have a problem to deal with this minus character here, which is known from the beginning, I think the paper from 91 with Arefjeva, Frampton, Volovic, and Dragović, and after that with Dragović with the signature change in the p-Adic case. Okay, so let's now deal with a more complicated but more physically interesting case. And in this case, the equation of motion will be given in this form. I hope that you remember the previous form, but just for let's say connection of the presentation, please give me to come a few slides before. So we have here the second derivative, we have the first derivative with the square here, and also we have here this square of the t dot. So this is a bit more complicated case, and in the case when we have the static space time, we have this kind of the form. So is it possible now to, let's say, to catch and to fight with this challenge? Here, just to mention that we use the Hubble parameter here in the form of the relation between scale factor and its first time derivative. So the transformation will lead us to the Lagrangian, which has this normally a free factor here, which appeared here, of course, because we have a co-moving space, co-moving coordinates, and the expansional rate of the space-times we are using here. So without some technical details, the following procedure is based on the applied Darboux method in our case. So the question is, can we find again an equivalent quadratic Lagrangian to the previous one? For this, we have to introduce the Jacobi multiplier in the form given here, and it can be done in all cases for all values of v in the character here, which means that we can do it for the real and any p. However, I told that in the beginning, unfortunately, till now, we are able to do it only for the p equal 1 modulo 4. So our initial equation now takes the following form. And again, the crucial problem is here with this guy here with the t dot square. So we have to find a way how to transform it in the quadratic case. So, using the Darboux method, we find that from Darboux method, our function a, which now consists of the tachyonic field t dot and time t, has the following form, and the lambda factor here is given with the with the scale factor, with the Hubble parameter, and with the square potential. Of course, if we have a non-dynamic system, we will have that this factor will be equal 0. So, using the canonical transformation, again we get the equivalent Lagrangian. However, because of this guy here with square, we want to see if it is possible to get it in a, let's say, nicer form. And for this, we introduced the new variable, phi dot, which belongs the relation between the first derivative of time of the tachyon field and the tachyon potential itself. It is valid for any kind of the tachyonic potential. For instance, if we present this change was given, this relation was given for the phi dot. If we integrate it in the real or p-adic case, we have that field, new field phi, which is related to the original tachyonic field T, has this Lagrangian. Again, we have this factor here, which is corresponding, to the scale factor of the space we are considering. And now we have the again we have the quadratic form of the Lagrangian with a canonical kinetic energy, and again with the potential now in this form. Of course, we can take some W potential as we did in some of our papers, but I prefer here to give it explicitly. Of course, now this Lagrangian is implicitly presented by the tachyon field. In fact, we have the new field phi, but the generality, I think, is not disturbed anymore. So we can choose some, and we choose some potential to test our model. And for instance, for the one of the most used potential in the string theory, which when we have the exponential potential for the tachyonic field, we got again the inverted harmonic oscillator, but now with the time-dependent mass. So the dynamic of the space-time here is encoded in this form of the mass of the corresponding mass particles or whatever here. Depends of the potential you use. You can have here also the frequency dependent case. So in our of the papers, Branko Dragović and me, we discussed the case with the frequency dependent harmonic oscillator, and here we have the mass dependent harmonic oscillator. After some calculation, we can find the trajectory, and we can find the classical action. Let me say, let me underline here that we can now make we can transfer from the three-dimensional or four-dimensional space-time to one plus one. Why? Because we choose the homogeneous and isotropic space, where the all space-like coordinates have the absolutely the same dynamics given by the scale factor A. So in this case, we can present all these variables and in the following form. So for the people who are familiar with that, we can see that it is a generalization of the time-dependent harmonic oscillator, but now with the repulsive nature, means that we have the invert harmonic oscillator. So depends of the original potential. We can have different form of the for the phase factor gamma, for instance, here, but this form is valid for any kind of the tachyonic potential we consider it. Again, we are able to get this implicitly. We have this prefactor here, and any any adelic character here. And let me repeat again that due to the form of the metric, it is valid for p equal 1 modulo 4. So at the moment we are not able to do the complete adelization of the model. Finally, I can say that the motivation for the further research is, I would say, very interesting one. Namely, we put these all potentials I mentioned in the machinery of the tachyon inflation, and we check out the results and compare with the data. So, starting from the standard Einstein's gravity and using the dBi Lagrangian that is presented here, we are able to get the Friedman equation of motion presented here, and then it goes to the system of nonlinear equation, which finally comes to the calculation of the slow roll parameters. We can calculate number of e-folds, and in the slow roll approximation we get the modified spectral index and tensor to scalar ratio. And here briefly I can present some of the old and some of the new results. I think I can skip this part of that because it's not so important. Much more complicated and more precise results we get through the so-called Randall-Sundrum model when we have the two d-branes, which dynamics of the d-brane is explained by the tachyonic potential. Then, so the tachyons practically mimics the dynamics of the d-brane, and it makes the repulsion of the d-brane. So the system is, let's say, pretty complicated nonlinear one, and the calculation has to be done in the numeric case. And here are some of the results. We present here the best fitting, which is almost perfect. Unfortunately, or honestly speaking, it is for a little bit bigger number of e-folds, but we also did in the holographic case, and it gives a pretty good results. So I would like to present some ideas for the further consideration of this model I present here, and related to the p-Adic sector. So first of all, the understanding of tachyon matter, we cannot be satisfied with that's for sure. And the perturbative solution for the classical particles that are analogous of the tachyons that I presented in the beginning, it's very challenging to calculate them, not only on Archimedean cases, that is done in some cases, but also on the non-Archimedean cases. So I speak about now of the classical case. So it's, generally speaking, it's not a problem. Reverse engineering method that I also presented leads us to the quadratic and canonical form, and which are locally equivalent to the original one. However, to give a definite answer about the equivalency of the corresponding action on, let's say, a longer period of time, what means longer in this case, that's a very tricky stuff, because we are speaking about inflation, which we know that it takes about 10 minus 35 seconds. However, this is still a challenging point. Also, the next point is that in several papers, in some cases, this original work idea by Barnaby and Klein was considered continued by Koshlev, Branko Dragović, and colleagues from Belgrade, Rakić, Dmitrijević, and Dmitrijević again. I think it is very interesting to see how our p-adic inflation model could be compatible with CMB. What is important here that now we have a possibility to quantize the tachyons in the p-adic case, at least for p equivalent 1 modulo 4. Finally, there are papers about attractor behavior of the originally based Dirac-Born-Infeld Lagrangian, and we approved that this maybe not all, because we don't have a general approval for that, but for the good part of the tachyonic potentials, we have the full attractor behavior. But it's not yet tested in the p-adic and adelic context, and I would like to learn and to consider in the future how we could apply it and to define the attractor behavior in the p-adic context. So this is I would say our plan for a part of our research. So the perturbation of the tachyon field on the p-adic space-time, and attractor behavior on the p-adic space-time, and after that also all of that unified in an adelic form. So there are a lot of things to be done, and there are, I would say, important but a less challenging idea. It is to present all these results in a full mathematically acceptable form for the all potentials, either with the inverse power terms or for the cosinus hyperbolic exponential one, etc. How anyway, this is the general form for the dBi Lagrangian in the expanding space-time for I say equivalent almost or locally equivalent quadratic Lagrangians in the form of the quadratic action and on the form of the kernel of the operator of evolution. So this is the basically what I would like to present today, and I think that it is that I was in time with the proposed and with the agenda of the today talk. So thank you very much, and I'm here for the eventually questions or possible questions. Thank you, Zoran, and thank you all for the following my lecture.